Indian Railways is striving to match the Indian economy's growth rate. It is also actively looking at doing so without waiting for new capacity creation. Hauling heavier trains and increasing the balancing speeds is an obvious solution. There is, therefore, a compelling need to increase the horsepower of our locomotives. Indian Railways had entered into a transfer of technology contract with Messrs. EMD USA in 1995, which, besides a transfer of technology for manufacture of 4,000 horsepower locomotives, also included a transfer of technology for EMD's 5,000 plus horsepower 20-cylinder 710 series engine. This clause had not been exploited because of axle load constraints. While worldwide the 20-cylinder engine is used with 30-ton axle load, IR had a limitation of 21-ton axle load. However, the 2710 engine was the ideal platform for enhancing the power of freight locomotives to 5,000 plus horsepower. Fortunately, a window was available a few years ago when the axle load was allowed to incrementally increase from 21 tons to 22.5 tons. This proved to be crucial in activating the latent TOT. It enabled development of a 5,500 horsepower freight locomotive. The new limits of axle load through the catalyst was not enough. It needed innovative initiatives like the Garib Rath profile, hybrid bogie, compact traction control system, use of stainless steel and an ultralight underframe to accomplish this task. The designing process of WDG5 was one of the most thorough ever undertaken by Indian Railway. It involved various stages: conceptual design review, detailed design review, para-solid generation of structures, finite element analysis of components, circuit analysis, multi-body dynamic analysis for bogie, solid modeling, routing, layouting, interference analysis, drawing generation, manufacturing review, final design. There were 3 conceptual design reviews held over a period of 6 months starting from October 2009 to select various subsystems. This was followed by detailed design reviews over the next 6 months to freeze the general architecture after integrating the major components. The general architecture of WDG5 was framed in September 2010. Post-finite element analysis validation, the detailed design activities were taken up by DLW. This included solid modeling of individual components, dimensional and clearance analysis, release of drawings and finalization of product structure with complete parent-child linkage. The product structure was released in December 2010. 2 manufacturing reviews were undertaken in March and July 2011, involving participation of various shops, potential vendor identified for manufacturing of the prototypes. The opportunity of a new platform was used to bring in several new technologies. On this locomotive, EMD EC electronically sets and adjusts engine fuel injection to produce the horsepower and engine speed schedule for the throttle setting set by the EM2000 locomotive computer. It eliminates a number of mechanical linkages and tremendously improves the response and feedback. Electronic fuel injection allows better fuel efficiency besides enabling reduced emission capability. The efficiency has been further harnessed by integrating the automatic engine start-stop feature. Tread brake units are bogie-mounted air-powered brake devices. They are a combination of brake cylinder, transmission mechanism and slack adjuster. Each bogie has 2 tread brake units fitted with additional saddle-mounted spring-actuated modules. These TBUs, in addition to working as service braking devices, also work as parking brake units. CCB2 is the latest state-of-art microprocessor-controlled air brake system. CCB2 brings in minimum number of interface controls, improved reliability, easy in maintenance and increase of overall periodicity. The GT locker, electrical locker, replaces the ECC1, ECC2, ECC3, TCC1 and TCC2 cabinets with a single cabinet while retaining the functionality. Essential building blocks of the E-locker will have significant improvement compared to WDG4 locomotive, including packaging of equipment into a single cabinet instead of 5 cabinets, reducing the cabling. It eliminates components such as battery charging rectifier and replaces the same with solid-state technologies such as auxiliary power converter, thereby improving reliability. Radial design DBR hatch assembly has been used in this locomotive. This compact and modular is requiring lesser space. The geometric configuration provides efficient heat dissipation. The locomotive has been designed to set up new standards for crew comfort and safety. The locomotive implements EN 12667 collision protection, provides for heated ventilation, air conditioning, has provision for a toilet, provides for a visual TFT-based driver display and an ergonomically designed driver seat. Though the locomotive is longer than WDG4, it is designed for better visibility through an enlarged MMD, elimination of the blower duct and a raised radiator profile. For certain items where we traditionally have indigenous competency, it was strategically decided to repose confidence with indigenous suppliers. DLW closely worked with the vendors at every stage, that is, framing of specs, understanding of the product through solid models, pre-production reviews, locating sub-vendors, sets up new processes, process reviews, stage inspections and final product inspection to get the prototype through in the tight timeline. Some of the items which were indigenously developed are underframe assembly, superstructure, cab, fuel tank, bogie, control console. DLW's facilities needed to be retooled for underframe manufacture, bogie assembly, deck milling, load testing and material handling. It was necessary to actively involve the shop personnel at the initial stage itself. It was also necessary to ensure that the teams develop ownership and develop solutions on their own. The leadership was shared between design and production. This resulted in a boundaryless working which shaved off months from the manufacturing cycle. With the vendor base spread across the world and with multiplicity of vendors across the continents, EMD, Dighton Phoenix, Knorr-Bremse, Zhaozhou, Tinken, to name a few, it was necessary to establish direct contact with their engineers and supply chain people. Design office took the lead to energize the contacts and also took over the role of material management. The extensive interaction resulted in the OEM suppliers shrinking their deadlines and even airlifting to accommodate the prototype timelines. Operationally, the locomotive provides for the highest starting TE on Indian Railways, 560 kN. It can start the iron ore loads which invariably move in graded sections at 1 in 150 grade. The locomotive, being blessed with the highest horsepower, will have balancing speeds of 100 km per hour for almost all the loads of IR. Even the heaviest load of 59 BOXN CC plus 8 plus 2 can be hauled at 90 km per hour. Further, the locomotive has also been designed with AESS to further harness fuel savings in the freight operations. The locomotive comes with the largest fuel capacity of 7,500 litres to provide long runs without refueling. WDG5 has been trailblazer in more than one way. WDG5 will deliver the maximum horsepower at the minimum line haul cost. It will provide the maximum TE on IR. It will provide a significant jump in balancing speeds. It will take crew comfort and safety to the next level, but it will also set many other standards. It will be the first locomotive to be designed with active cooperation of the OEMs. It will be the fastest prototype from concept to rollout within 2.5 years. It will also be the fastest prototype to be manufactured by DLW in 4 months. As we look back, we realize that there's a need to dream. There's a need to push conventional constraints like maximum moving dimension and axle load to fulfill our dreams. That given a passionate and innovative approach, we deliver the best to the nation.